8.3 Proving statements involving matrices. You can use matrix multiplication to prove results involving powers of matrices. Now, of course, just as a reminder of the steps involved with a proof by induction problem, shown here, our first step is the basis step where we prove the general statement is true for n equals 1. We then move on to our assumption step where we show the general statement is true for n equals k. We then move on to our inductive step where we show that the general statement is then true for n equals k plus 1. And then for our conclusion step, we show that the general statement is then true for all positive integers n. Now, as we saw with the summation proof by induction problems, I think it's a good idea to actually show before you proceed any further what exactly you want to show. In other words, write down your goal. Example number 7, we have to prove by induction that for all positive integers n, the matrix 1 minus 1, 0, 2 to the n equals 1, 1 minus 2 to the n, 0, 2 to the n. Now, just as we saw with the series proof by induction, our goal over here is to replace the n with k plus 1 and show the left hand side is equal to the right hand side. Now, what do I mean by that? We want to show this result here. Now, all that's happened here is the n has been replaced with k plus 1, and somehow when we do our inductive step, this is what we want to show. So with our first step, just as a reminder of what our first step is, we need to prove the general statement is true for n equals 1. So for step 1, we want to show that when n equals 1, the result is true. So if we substitute in n equals 1 on the left hand side, we have 1 minus 1, 0, 2 to the power of 1. Of course, that's quite easy to work out. That's just 1 minus 1, 0, 2. And on the right hand side, if we substitute in n equals 1 here, we've got 1, 1 minus 2 to the 1, 0, 2 to the 1. And if we work this out, well, here we get 1, here we get 0. 1 minus 2, that's minus 1. 2 to the 1, that's just 2. You can see the left hand side is equal to the right hand side. So you can see here, since the left hand side is equal to the right hand side, the matrix equation is true for n equals 1. Now, for our second step, we need to assume that the result is true for n equals k. So just as a reminder of what step 2 is, that's the assumption step. We need to assume the general statement is true for n equals k. So if we do that, we have this result over here. 1, 0 minus 1, 2 to the k is equal to 1, 0, 1 minus 2 to the k, and 2 to the k. So all that's happened here is n has been replaced with k. And that's what we do with our assumption step, okay? Now, our third step, which is the inductive step, we need to see what happens, as we see over here, when n equals k plus 1. So, when n is equal to k plus 1, now bear in mind what exactly we want to show. We want to show that this result over here is equal to this over here. So, we have 1, 0, minus 1, 2 to the power of k plus 1, and we need to somehow show that this result here is this result here. Now, we can use matrix multiplication to rewrite this. So we've got 1, 0, minus 1, 2 to the k, lots of 1, 0, minus 1, 2 to the 1. Okay? And of course, with the same base, we add the powers, and if we do that, this result is definitely correct. So now we just need to use matrix multiplication. Well here, this result here, using our assumption step, that's equal to 1, 0, 1 minus 2 to the k, and 2 to the k. This result here is what we have over here, 1, 0, minus 1, 2. And now if we expand all of this out, a 2 by 2 times a 2 by 2, that's also going to be a 2 times 2. So here we've got 1 times by 1 plus 1 minus 2 to the k times by 0. So that's this element here. For this element here, we've got 1 times minus 1 plus 1 minus 2 to the k times by this 2. For this element here, we've got 0 times by 1 plus 2 to the k times by 0. And for this final element, we've got 0 times by minus 1 plus 2 to the k lots of 2. Okay? So now we need to tidy all of this up. You can see on the top over here we've got 1, here we've got 0, now here we've got minus 1. Now we've got, as well, if we expand all this out, we've got 1 times by 2, that's 2. And then we've got minus 2 to the k times 2. Of course, adding the powers because we've got the same base, that will be minus 2 to the power of k plus 1. Okay, so all that's happened over here is we've assumed that 2 can be written as 2 to the power of 1, and that's what we'll do here as well. Okay, and for this final element we've got 0 plus 2 to the power of k plus 1. Again, we've got the same base, we add the powers. So if we tidy all this up, we've got 1, 0. Here we've got minus 1 plus 2, which is 1. And then we've got the minus 2 to the k plus 1. And here we've got 2 to the power of k plus 1. So that's what we do for our third step. And indeed, that's exactly what we have over here. So now we can move on to our conclusion step, step 4. And with our conclusion step, we would have the following. If the matrix equation is true for n equals k, then it's been shown that it's true for n equals k plus 1. And as the result is true for n equals 1, it is also true for all positive integers n. Example number 8, we have to prove by induction that for all positive integers n, minus 2, 9, minus 1, 4 to the n equals minus 3n plus 1, minus n, 9n, and 3n plus 1. And I think when we begin any proof by induction question, it will be a good idea to write down the aim, our goal. What do we want to show? We want to show this result over here. We've got minus 2, 9, minus 1, 4 to the power of k plus 1. This is equal to minus 3 lots of k plus 1 plus 1, 9 lots of k plus 1, minus, and then in brackets k plus 1, and 3 lots of k plus 1 plus 1. Essentially over here, the n's have been replaced with k plus 1. Now, with our first step in a proof by induction question, we'll see what happens when n is equal to 1. So we substitute into the left hand side and the right hand side, and let's see what we get. So on the left hand side, we've got minus 2, 9, minus 1, 4 to the 1. This is equal to minus 2, 9, minus 1, 4. Okay? And on the right hand side, if we replace the n with 1, we have minus 3 lots of 1 plus 1, minus 1, 9 lots of 1, 3 lots of 1 plus 1. So minus 3 plus 1, that's minus 2. 9 lots of 1, that's 9. Then here we've got the minus 1. 3 plus 1, that's 4. You can see the left hand side is the same as the right hand side. So therefore, as the left hand side is equal to the right hand side, the matrix equation is true for n equals 1. And then we move on to our second step, the assumption step, where we will assume that the result is true for n equals k. So we will assume that when n is equal to k, we've got minus 2, 9, minus 1, 4 to the k. That's equal to 3k plus 1, 9k, minus k, and 3k plus 1. So when we move on to our third step, our inductive step, we see what happens when n is equal to k plus 1. So we've got minus 2, 9, minus 1, 4 to the power of k plus 1. Now we can rewrite this using the laws of indices as minus 2, 9, minus 1, 4 to the power of k, lots of minus 2, 9, minus 1, 4 to the 1. Same base, we add the powers, we get this result here. So now we need to use matrix multiplication to simplify all this. Well, first of all, this result here, using our assumption step, we have minus 3k plus 1, 9k, minus k, and 3k plus 1. And we multiply this by minus 2, 9, minus 1, 4. So now we need to simplify all of this. So if we tidy all of this up, multiplying everything together, we have over here, well, let's write it out in full. We've got the minus 3k plus 1, lots of the minus 2, plus the 9k, lots of the minus 1, that's for this top element. For this element over here, we've got minus 3k plus 1, lots of 9, plus 9k, lots of 4. This element, we've got minus k, lots of minus 2, plus 3k plus 1, lots of minus 1. Okay, that makes sense. And here we've got minus k, lots of 9, plus 3k plus 1, lots of 4. So if we tidy up the top, we've got minus 3k times minus 2, that's positive 6k. And then we've got the 1 times minus 2, that's minus 2. And then here we've got minus 9k. Here we've got 9 times by minus 3k, that's minus 27k. And then we've got 9 times by 1, that's 9. And then we've got 36k as well. Here we've got minus k times by minus 2, that's positive 2k. And then here we've got 3k times minus 1, so that's minus 3k. And then here we've got 1 times minus 1, that's minus 1. Here we've got minus 9k. And then we've got 12k plus 4. So now if we simplify all this, we've got 6k minus 9k, that's minus 3k. And then we've got the minus 2. Here we've got minus 27k plus 36k, that will be 9k. And then we've got the plus 9. Here we've got minus k minus 1, and here we've got 3k plus 4. Now, is this the same as this result here? Well, clearly it is, because if we expand this out, we get minus 3k, and then the minus 3 plus the 1, that's minus 2. So that's what we get in this element. Here, 9 lots of k plus 1, expanded out, that gets me that. Minus and then k plus 1, that gets me the minus k minus 1. And 3 lots of k plus 1 plus the extra 1, that's 3k plus 4. So we've got the right result over here. So after this, we write down what we want to show, which is we have minus 3 lots of k plus 1 minus k plus 1, 9 lots of k plus 1, and 3 lots of k plus 1 plus 1. This is what we wanted to show. So we can see here that the matrix equation is true for n equals k plus 1. So now for our fourth step, we have our conclusion step. So if the matrix equation is true for n equals k, it's been shown to be true for n equals k plus 1, and as the matrix equation is true for n equals 1, it is also true for all positive integers n.